Related rates questions are some of the trickiest questions that Cal 1 students encounter. And so I'm going to show you a 5-part process that will help eliminate some of the confusion attached to related rates. The first part of this process is that you have to draw a picture.
As an example to follow these steps, here I have that oil spilled from a ruptured tanker spread in a circle whose area increases at a constant rate of 6 miles square an hour. How fast is the radius of the spill increasing when the area is 9 meters squared? Alright, so sometimes we have a hard time getting started with this, so as I said, the first step of this process, one, is just simply drawing a picture. And so here I have a tanker. Okay, the boat doesn't have to be too detailed, and there's an oil spill coming around. And what I know is that the area, so this is kind of denoting that change in area here, is this spreading out at 6 miles squared an hour. Okay, I also know that the area at a specific moment in time is 9 miles squared, and I'll say at a given moment.
Secondly, what we need to do is identify what's known to us, what's constant, and what we are looking for.
Now moving on to part 2, I want to identify, first of all, what's known to me. So what do I know? And this is where we have to be careful. Anytime you see this phrasing, rate or a change, instantly you should think derivative. So what I know is that rate of change is a change in area. So my dA dt is 6 miles squared an hour. You can also tell by the units when you have some sort of unit of measurement divided by a unit of time, that denotes a derivative, that's a change. Okay, I also know the area is 9 miles squared at a certain moment. Okay, so that area is changing obviously as the spill gets bigger, but that's what I know. And then what am I looking for? And this is something that a lot of students really struggle with. So that's why we bother writing it out. What am I looking for here? I'm asking how fast is the radius increasing? Again, fast is a word to denote change. So what I'm looking for is a change in radius with respect to time. Okay, so my picture here, maybe it'd be useful if I denote, okay, I have some sort of radius here as well.
Part 3 is why we call this related rates. It's difficult to relate the derivatives that they've given us compared to the derivatives that we're looking for, but what we can relate are the variables themselves. So we need to find some sort of formula, either through geometry or trigonometry or through algebra, that relates the parts that we need in order to find the derivatives we're looking for.
Now for part 3, this is where we get into the idea of related rates. I'm trying to relate the change in area to the change in radius. I didn't learn any formulas in geometry or in high school that talk about the relationship between a change in area and a change in radius. But what I do know is a relationship between the area of a circle and its radius. So I'm going to use that. I'm going to use area equals pi r squared.
Fourthly, now that we have found the correct relationship between the parts that we need, we can use implicit differentiation to introduce the rates and identify the rate that we're given and the rate that we're looking for. Now, as a warning, sometimes if you take the derivative and you introduce a rate that you do not know, you need to backtrack to figure out a way to eliminate that variable before you do implicit differentiation.
Now for part 4, I'm going to introduce implicit differentiation. And so I'm going to take the derivative of both sides with respect to time. So that means I have to treat a and r as functions of time. So the derivative of pi r squared is 2 pi r, but you can't stop there. It's 2 pi r times dr dt. Again, the radius is a function of time. Okay, now what I know is I know this. I'm looking for that, the dr dt, and I don't quite know the radius. So I can go back, though, to part 2 over here and remember, okay, I know that the area is 9 miles squared at that specific moment. So using my area formula, I know that 9 equals pi r squared, or 9 over pi equals r squared. So then that means r would have to be the square root, technically plus or minus the square root of 9 over pi, which is plus or minus 3 over square root of pi. The thing is, though, we're talking about a radius, right? So it doesn't make sense to talk about a negative radius. So here we just have positive 3 over square root of pi. So now I can plug in my values. And what I actually like to do first is I actually like to solve algebraically for the thing I'm trying to solve. So in other words, I need to get the dr dt by itself. So I'm going to divide by 2 pi r. So I have 1 over 2 pi r equals dr dt.
Finally, in part 5, all we need to do is plug in what we know and solve for the rate that we don't know.
Okay, lastly, all I need to do is solve or plug in my value. So I know that dA dt is 6. I have 1 over 2 pi times 1 over r, and 1 over r is simply the reciprocal of what I calculated for r. So the reciprocal of that is square root of pi over 3 equals dr dt. And I just need to solve the left-hand side of my equation here just to get my answer, okay? So what I notice is in the denominators I have a 2 and a 3, which multiplies to give me 6. So actually, the 6, the 2, and the 3 cancel out. And I can also cancel out pi and square root of pi and be left with a square root of pi in the denominator, right? Because isn't pi the same thing as the square root of pi quantity squared? And so that's what I did here. So what I end up with is 1 over root pi d equals dr dt. And we should actually have some measurements here, okay? So this is 1 over square root of pi. What is my change in radius? Is in miles per hour. Okay, so 1 over root pi miles per hour is my change in radius.
Related rates can be tricky and it requires some work. You need to encounter several different examples in order to feel secure about how to approach these problems. If you have any questions though, please let me know. I'd be glad to help, and thank you for watching.